Hello everyone, I am Tistapal and I am a master's student at the Graduate School of Software and Information Science at Iwate Prefectural University in Japan. I am majoring on AI and today I am honored to be presenting my work at the 19th International Conference on Advances in Computer-Human Interaction 2026. My paper is titled Memory-Driven Person Re-Identification for Identity Consistency in Multi-Object Tracking. Before we begin, I would like to introduce myself a little bit more. So, my research interests lie in image processing, computer vision, object detection, and deep learning. The work I'm presenting today sits right at the intersection of all these areas, and I'm very excited to be able to share it with you. Now, let me walk you through the motivation behind this research. When we track people across multiple video frames, a fundamental problem arises with traditional multi-object tracking relying on short-term cues. This means they often lose track of a person's identity the moment they are occluded or temporarily leave the camera's view. So our goal is to design a tracking pipeline that maintains global identity consistency across time and video frames. And so as we can see here, so maybe this person have initially having a ID 5, and then as soon as there's another person with similar clothing and then features, they appear and then they occlude that the original person, they are turned into ID 8. And what our goal is to keep, even after occlusion, the main person should remain as it is as they were assigned initially. So the current challenges existing in this field are similar clothing, with a huge crowd having similar clothing, especially during the office hours. People tend to wear some formals which looks somewhat similar like a uniform. That leads to a big problem. And then when there is environmental factors such as bad lighting or shaky camera, and also occlusion when the person is hidden by some object or maybe some other person. And then also orientation change. So if the person currently here we can see they are given ID 1, and as soon as their body orientation changes, their ID also changes. So these all leads to one solution, but these all can be solved using one solution, which is person re-identification. That is identifying the same person again and again so that we can keep their identity consistent. So our goal is to design a tracking pipeline that maintains the global identity consistency across time using the long-term appearance memory. So before we begin, a short introduction to what exactly re-identification means. So if we encounter a person in a video frame, say X, at t equal 1, and then we want to keep tracking the same person, but the person goes missing in the in-between frames at t equals to 2 or t equals to 3, and then again reappears at a video frame at t equals 4. So this person and this person is same, and my or our model should be able to keep the identity same as assigned initially. So what we are dealing is with a single camera that is trying to keep the identity consistent in all the video frames, but it has other usage in like multi-camera when we have several cameras, and then we try to keep tracking the same person throughout different cameras. So the basic pipeline would be like, first we detect the object, then we track them and then assign them some ID. And if the person goes missing in the cameras or in our project, if it goes missing in some in between video frames, then we should be able to re-identify them again when they reappear with the correct identity. So a real life example would be this technology could be used in tracking suspicious person. If someone is roaming around our house, or if there is a robbery and then we want to find the culprit, then we could be able to find the suspect easily. And then if there is a person who goes missing, then we could track that person, and using the re-identification, the using assigning IDs, we could easily find them out in a crowded situation. So another use case will be in airports, where we want to like check like for high security areas. Of course, we want some kind of good tracker to track people, so that we can have a track of no illegal activities going on. And then also we can do crowd analysis using person re-identification, and then we can manage the crowd in a huge space like concerts or stadiums, or yeah, big areas like that. So in person re-identification, of course, we need a good tracker to track the people. And for our project, we will be using deep short. We already had short, but the key point in deep short is it gives us like the CNN feature extractor, and it's based on appearance based module, so which gives us a plus point because the deep short also output local track, which I will explain further how we use the local tracks in this project. For feature extraction, we would be using the very well-known two feature extractors, OSNet, the Omni-Scale Network, and then ResNet Residual Network 50. And ResNet, we all know, is a very good model in the field of computer vision and image processing. But we will also be exploring the OSNet, which is like a very lightweight model than the ResNet, and then it also focuses on omni-scale. So it also focuses globally, but also it takes care of like small things. Like for example, in this picture, we could see a person with a bag and the cap, and then omni-scale network can distinguish the features of the bag and the cap and then pants. But whereas ResNet is focusing globally. Similarly, the kid with the cycle, we could see that OmniScale network focuses on the small cues of the cycle, whereas ResNet focuses globally. So we are trying to see both the we will be trying to explore both the models in this project. So the memory-based re-identification already exists with cross-camera re-identification, and for this project, we are going to try on the single camera based re-identification. And for most of the memory-based re-identification, the memory size is often fixed, and then the real-time tracking still remains unexplored with global identity memory. So we will try to explore few things with the global identity memory. For the dataset, we are using the MOD17 dataset, multi-object tracking challenge format. And we chose this dataset because it gives us multiple pedestrian video, like a real life scenario. And then it also captures like the challenges we talked earlier about, like varying illumination, crowd density, camera motion conditions. And for this particular project, we choose these 5 samples out of all the existing samples because some of the samples were like filmed from a bus and didn't really had so many people. It was just car, and then our project only focuses on uh, personal identification. So we choose these 5 that suit best for our project, and we took the video frames of these 5 uh, data set. And out of all these, I think the 04 and 02 were the most challenging one, and our model could perform well in the 04 and 02 as well. So as we discussed earlier, the pipeline, the first thing comes the object detection, the detecting of the people. So we have these video frames, the input image, and then what we are doing is using yellow version 8. We are trying to create bounding box, and then we are also applying the segmentation masks, and then we put the both of them, like masking the segmentation mask on top of the actual image, and then we are trying to feed that into the feature extractor. But a drawback of this paper is that the feature extractor is not really mask aware feature extractor, so this didn't really add up to a lot, like really add up much to the improving of the feature extractor. Comes our main star of the show, that is the global ID module. And what we are doing here is the object tracker in our case it's deep short. It produces its own local track ID using the Hungarian algorithm, and then appearance, similarity, and IOU, intersection over union. And then we are feeding the local track as well as the feature embeddings into the global ID bank. And the ID bank is designed in such a way that maximum there will be 20 embeddings per identity. And then we decide whether there is, and how do we keep this 20 embeddings? We decide if it's the similarity is greater than the threshold that we set up. We will explain the whole pipeline in the next slide. And if it matches it, if it's equal or greater than the similarity, we assign them the same ID, and then we update here our embeddings using the exponentially moving average. And then if it doesn't match the similarity threshold, then we assign a new ID and create a new ID. And then if the entries remain unmatched for more than 30 frames, then we consider that that person is no longer present in the video, and we remove them from the gallery to make it more to make the memory less used. And then we move on to the next frame. And so the complete pipeline looks like this. We have the MOD17 video frames. Those are input to the object detector, and then the object detector produces its yellow bounding boxes and then segmentation mask. And then those bounding boxes or cropped images goes to the feature extractor as well as object tracker. I'm so sorry, object tracker deep short. And object tracker produces its own CNN using its own CNN feature extractor. It produces its own local tracks, and our feature extractor, the OSNet or ResNet, also produces its own feature embeddings, though that gets saved into our global ID memory. So it has, and then also the local tracks, we match it using the Hungarian similarity matching, and then we check if the embeddings and local tracks present in the global memory are passing our similarity threshold at is 0.8. If it does, then we assign them the same ID. If it doesn't, then we assign them the new ID. And for our feature extractor, it is pre-trained using we are using the pre-trained weights of the Duke MDMC and the Market 1501 data sets. And yes, so this is our result, and we could see we used just the deep short CNN descriptor, and then the yellow version 8 for our baseline, and it was the original IDF1, and this is our proposed filtered IDF1. I will explain it in the later slides. And we could see using the global ID memory, we have a huge difference between the baseline and then our proposed method. And here the OSNet Duke MDMC means our feature extractor was pre-trained with these weights, but the trade-off with the accuracy of the ID switching, and then the trade-off with the ID consistency, and then the FPS is very bad. We cannot consider it as real time yet. And the IDF1 is being calculated as true positive, that is the detection that matches the ground truth box and the assigned ID, and both location and identity are correct. The false negative means a ground truth person that your tracker missed entirely, or tracked with a fragmented wrong ID. False positive means like our tracker output a detection that has no matching ground truth person, or the ID was assigned to the wrong person. And our proposed filtered IDF1 means that IDTP detected is like the identity true positives among the only the detected ground truth identities, and then these are the false positives associated with those same detected ground truth identities. ID switches, ID SW is ID switches, so the ID switches among the detected only ground truth. So when the tracker swaps the ID of a person, it was tracking correctly or not. And then the motivation for our filtered IDF1 is, with the current traditional IDF1, it measures how well the identities are preserved over time. But if the object detector misses any ground truth identity, then the deep shot will be penalized for that. So when yellow misses a person, that person does not enter deep shot or OSNet ResNet, but IDF1 still penalizes the system. So we don't actually getting any feature vector using deep shot or OSNet, but still the IDF1 is penalizing. So it is like the fault of the detector, but we are penalizing the fault of a feature. We are penalizing the fault of overall fault. So if a person in ground truth is never detected, the tracker is still penalized. This includes identity switches that deep shot could never fix. And for so we then propose the filtered IDF1, and we calculate the IDF1 only for the detected person by yellow to isolate the re-ID tracking performance. So where instead of false negative, we change it to ID switches of only the detected IDs. This avoids punishing tracker for detector weakness. So this is our result, one of the result. And if we focus on this person, global ID1, we could see that even if they are occluded, and they still keeps the ID same, and throughout the video, if they are occluded for a longer period of time, also they keep the ID same. And similarly, this person as well, when other people try to occlude them, so if we see some person coming, the ID 24, and then it occluded, so it still remains same. Conclusion of this project is the feature embeddings plays a very important role in person re-identification. Therefore, managing and storing them makes the difference in ID consistency. Segmentation masks does not play a significant role in improving the identity consistency if the feature extractor is not mask aware. A strong global ID bank keeps the feature vector and time to time update the feature so that the features of that identity can be more generalized, leading to more stable identity assignment. So some of the limitations is the current re-identity backbone doesn't work well with the segmentation mask. And what we are planning to do in future work is to make the re-ID backbones mask aware. And the second problem would be the detector causes the original IDF1 scores to decrease. So we will try to make the detector more powerful so that we could use the original IDF1 score without compromising. And the third will be the current pipeline is computationally costly because we have this global ID module and deep short CNN feature extractor. So we will try to keep the we will try to alternate uh, tracking methods, alternative tracking methods, and maintaining the feature vectors in a better computationally efficient way. Thank you so much for listening to my presentation and giving me the opportunity to share my work with you. I hope you have a good day.